Hello everyone, I'm Sajad Hussain and my group member is Izzat Khan. Today we are discussing about our final year project load flow and contingency analysis of SEPCO region based on NEPRA Grid Code using PSS. This project is supervised by Dr. Fahim Akhtar Chachar. The agenda of this presentation is introduction, motivation, problem statement, literature review, aims and objectives, methodology, results and discussion, conclusion, future recommendation, and references. Introduction. Basically, a reliable and continuous supply of electrical energy is an essential part of today's complex societies. In recent years, what happens that power systems are operate closer to their limits due to different reasons like an increase in energy consumption or extension of existing transmission system. So a power system is said to be secure when it remains under the specified limits after being subjected to different contingencies or disturbance. And maintaining power system security is one of the challenging tasks for the power system engineers. So different security assessments are performed in order to get the complete information about the outage of electrical element and contingency in the system. To achieve that secure and economic operation of entire system, what we do is that we perform different simulation studies in order to know the facilities necessary to assure a system that is reliable and continuous in future. In this project, basically, we have conducted different simulation studies like load flow analysis, contingency analysis, and PVQV analysis, and different studies, fault analysis, and dynamic analysis for SEPCO region. Motivation. Basically, a reliability and stability is one of the important aspects of any system. There are different planning studies are carried out in order to know the response of system, how that system responds in case of any contingency, whether the system remains stable or not. And we identify different factors, and like we identify weak buses, we identify the violations of active and reactive power and voltages, and we find the steady state limits of these. So, and these all planning studies are carried out for SEPCO network. Problem statement. All these simulation studies are carried out for SEPCO, as we know that SEPCO grid is main part of national system. So if there is any change in national system, how that change will affect the SEPCO. So we have carried out all these study for that reasons. In these analysis, in this project, we have basically conducted two types of studies: steady state stability analysis and dynamic stability analysis. In a steady state, basically we have calculated different studies like PV and QV curves, load flow analysis, contingency analysis, and in dynamic stability analysis we have checked three things: voltage stability, rotor angle stability, and frequency stability. And all these are followed by the grid code limits that are defined by the NEPRA. Literature review. Basically, these are the papers that we have gone through and gained knowledge about our project and made and understood our project in a better and effective way. Aims and objectives. There are different aims in our project, but our objective is to conduct the steady state and dynamic analysis in order to improve the reliability of the SEPCO. We have conducted all these simulations for SEPCO region, and there are different aims like these all studies are based on actual NTDC model and actual NTDC data, and these are performed in PSS software. Basically, these studies help planning engineers in great deal, like to identify the weak buses of any network, to identify the violations of any network, and so that they may suggest solutions accordingly. And these and PVQ analysis is basically performed in order to overcome the voltage stability problems. And so as dynamic analysis is done to protect the system in case of any severe disturbance. And fault analysis is also done in dynamic simulation. Critical clearing time and critical clearing angle are also performed in this project. This is basically flow of our project from start to end. Methodology. In methodology, what we have done is that we have collected the data from NTDC network and filtered out the data of SEPCO region, for which we have to conduct simulation studies. So we have filtered out the data of NTDC to SEPCO, and we have conducted the simulation of SEPCO network. After conducting simulations, we have analyzed the results. We have highlighted the violations, and we have highlighted the weak grids in the SEPCO network, and accordingly we have suggested different solutions for that. This is a single line diagram of our network that we have conducted all these simulation studies on. So there are different simulation studies conducted on this network data, and we have formed the single line diagram of that network data. This is basically a PV curve. We have done PV QV analysis that was part of our steady state simulation of our project. In this curve, basically we check the response of voltage and active power. And basically in this project, we have done the PVQ analysis in order to know the loading limits of any bus. If we can see that this graph, what that graph shows, this is the point where if there is any change in any change in active power, after that change, if there is any increase in active power, the voltage might collapse. So this in PV curve, what we find is that we find that when there is any, we find the critical point. After that, if there is any change in active power, that change will result in voltage collapse. So in this case, this is the best case. In this case, there is no disturbance in the system and the voltage response is checked after power increase. As we increase the power, there is the point that voltage might collapse. So if we find that point, and that point is called nose point. And this is the single line contingency case. In this case, basically a single line contingency means that outage of any line generation unit from the system. So we have checked the response in that scenario in case of any contingency. Previously, we find that the system was intact. The system was intact. So in this case, we have created a contingency. So in this case, we also find the response of active power and voltages, and there is a critical point called nose point. After that point, if there is any increase in active power, that will result in voltage instability or voltage collapse. This is the QV curve. Basically, in QV curve, we see that how variation in reactive power injection at a bus affects the voltage of the same bus. It shows the relationship between voltage and reactive power. The amount of reactive power we inject at the bus, when there is a point at some instance where if there is any further injection of reactive power, then it will result in voltage collapse. So we have done, this is the best case basically of study bus 81302, and in this we have found a value of reactive power. After that value, if there is more injection, then voltage might collapse, and it is the maximum value of reactive power. And this is a single line contingency case. And so in this case, we find that Q minimum minus 35.937 is the maximum value of reactive power. After that, if we inject more reactive power, then it may cause voltage instability problems. So these are the basically PV curves that are used to find the voltage instability, and these are used to find the critical voltages, critical points. After that, if there is any increment, then the system's voltage might collapse. After these studies, we have calculated the dynamic simulations of our system, our network. So in this case, we have basically designed, we've taken three scenarios. In case one, we have given the fault at 100 milliseconds to the buses that are part of our network. So in this case, we have checked the three responses of rotor angle of buses, frequency of buses, and voltages of buses. And we have to check whether the system remains stable or not. In first case, we have kept the fault at 100 milliseconds and check the response. Now we can see that the rotor angle response of this bus called Liberty is initially unstable. After some time, it gains stability. And we can also see that the same response of frequency, that is after initial disturbance, it becomes stable. And for voltage, it is initially unstable, and after some time it becomes stable. So we have given fault at 807 bus and for 100 milliseconds, and we have tripped the line 8071 to 8072 and check the response of system. Either the system is stable or unstable. So in this case, the system is stable when fault is 100 milliseconds. And we have taken three scenarios of each. We have taken different buses for the same fault time, 100 milliseconds. And in this case, we can also see that the system response is stable after some initial disturbances. The frequency response is same as stable, and the voltage response is also stable. When fault time is 100 milliseconds, this is the first case and third part. In this case, we have also given fault to different buses of our network. When fault is applied at 8237 bus for 100 milliseconds and corresponding line 8090 to 8237 is tripped, then the system remains stable. We have checked all these three responses: rotor angle response, frequency response, and voltage response. Now in case 2, we have increased the fault time to 150 milliseconds. In this case, we have checked all these three responses, and we have repeated the same process of checking all the responses: and rotor angle response, voltage response, frequency response. In this case, we can see that as we apply the fault to 807 bus for 150 milliseconds and trip the line, corresponding line, then the system remains stable after some initial disturbances. Basically, we have to check the stability of the system. As we increase the fault, we might conclude at a point that the system might become unstable. So in second case, we have checked the responses of all these three power system parameters, and we have checked whether the system remains stable or not for 100 milliseconds fault. And this is the second case. In this case, we have also checked the responses of three different buses. In this case, we can also see that all these three responses are stable after some initial disturbances. And we have repeated the same process to apply fault at 8089 bus and trip the line 8089 to 8090 and check whether the system remains stable or not. In case 2, this is the third part. In this case, we can also see that all the responses of rotor angle, voltage, and frequency are stable. And these all responses follow grid code limits. This is the third case. In this case, we have increased the fault time to 200 milliseconds. In first case, basically, we gave the fault for 100 milliseconds and we increased that fault time to 150. And in third case, we have given the fault time of 200 milliseconds and we check the response of the system. So in this case, we can see that all the response of rotor angle response of Liberty and 4G fertilizer is unstable as we apply the fault at 807 bus for 200 milliseconds. And same case with voltages, the response of voltage is also unstable, and same as frequency response. So as we increase the fault time, the system might become unstable. And this is this case 3 part 2. In this case, we have also seen that the rotor angle response of Liberty and Ghotki is unstable after we apply the fault at 8089 bus for 200 milliseconds. But the voltage response of Liberty and 4G fertilizer is stable after some initial disturbance. This is the possibility that one might be stable, other might be unstable. So this is basically a possibility. And in third case, part 3, in this case, we can also see that the rotor angle response of Liberty bus is unstable, and voltage response of JDM GSM bus is stable, and the voltage response of Prialo is also stable, and the frequency response of this 4G fertilizer bus is unstable. So if we conclude that what we have studied in dynamic simulation, basically we have applied the fault for different time intervals and check the stability of the system, whether the system remains stable or not. So in first case the system was stable, but in second case it was also stable, but as we increase the fault time to 200 milliseconds, then the system was unstable. And there can be a possibility that whether voltage might be stable or frequency might be stable, but rotor angle might not be stable. So this is the dynamic simulation results. Now conclusion. Basically, we have performed the steady state and dynamic stability studies for SEPCO region. We have identified weak buses where voltage violations occur. In a steady state, basically we have performed PV and QV analysis, and we have checked the steady state limits for voltage and active and reactive power at different locations of SEPCO. And dynamic analysis, it was found that the system remains stable as the duration of fault is less, and it becomes unstable as we increase the duration of fault, like we have witnessed that before. Future recommendations. Basically, all these simulation studies were conducted for traditional machines like synchronous machines. So in future, what we can do is that we can go for the renewable generation, renewable integration, and perform all these simulation studies on these machines. And we perform the n-1 contingency. So in future, we can also perform the n-2 contingency